All right, picking up where we left off at 63. Says, find out how long it takes a $2,800 investment to double if it is invested at 9% compounded quarterly, round to the nearest tenth of a year. Use this formula. So find out how long it takes. So we're going to be finding T if we invest $2,800. So in our formula, that will be P. To double, well, to double would be 5,600, and that would be our A value. So that's A. If it is invested at 9%, so in our formula, that's going to be our rate. We change it to a decimal, 0.09. Compounded quarterly. Quarterly means 4 times a year, so that's our N value, so N is 4. And then we're going to round to the nearest tenth of a year. And we're going to use this formula. So it's a good idea to deconstruct the problem, which we did, or decode. So now I'm going to come over here because I don't think I have enough room. I know I don't have enough room. Here's the formula, and then I'll access the information that I have. So we want $5,600. I'm investing $2,800. It's our P. 1 plus, and then in our fraction, we're going to have 0.09. N is 4. And then up here, we've got N again, so that's 4, but we want to find T, so that's 4T. All right, what's interesting about this problem is we're finding T, and T is in the exponent position. So how do we find the T value? Well, the first thing is we're going to actually divide out the 2,800 into the other side of the equation. So let's get rid of 2,800. And as we should think, right here, 5,600 divided by 2,800 is a doubling situation, or a 2. So these will divide out. Okay, so now if we're going to be solving for T, we've got to get T out of this exponent position. And when we solve these type of problems, the way to bring T out of this exponent position is if we bring in an ln or log, doesn't matter. Just make sure it's the same on both sides of the equation. Let's bring in an ln on both sides of this equation. Okay, so I inserted ln, and now we have log properties that we can use. And we have a log property that says a power can come to be a factor. So what I'm going to do in my next step is I'm going to move that 4t in front of ln. So now we have 4t times ln of quantity 1 plus 0.09 divided by 4. If you want to, you can calculate that to be a decimal. You can find this value right here and add it to 1. It might make your work a little bit easier in the calculator. I'm actually going to wait till the very end before I put anything into the calculator. But again, like I said, you could go ahead and compute that if you want to. It might make it a little bit easier. Okay, now we want to solve for T. Well, 4 times T times this number, whatever it is. Let's get T by itself by dividing this 4 out and dividing this other factor of ln of whatever number this is. So I also have to divide out that 4 ln over here as well. So this factor will cancel here, and this 4 will divide out with this 4. And so we're going to have T equals this ugly expression. And I'm going to actually put T on the left-hand side of the equation. Okay, at this point, this is all calculator work. Just be careful. You know, you're going to take ln, make sure and put it in parentheses, and then you'll hit the division symbol, and then make sure and put this whole denominator in its own parentheses as well. Okay, and like I said, right here, it might make it a little easier if you change that to a decimal. Okay, and when you finish doing all that, if it's done correctly in the calculator, rounded to the tenth of a year, we're going to get 7.8 years. Okay, let's take a look at 64. All right, it tells us the formula A equals 173 times E raised to the 0.046t. This formula models the population of a particular city in thousands of people, t years after 1998. So when will the population, at what time, so we're finding t, when will the population reach 329,000? And that is our amount. Okay, so let's record that formula and then insert our quantities. Okay, so we want the amount of the population to be 329,000. E raised to the 0.046t. So that's the only thing we had to insert was 329,000. So now we need to solve for t. So the first thing let's do is let's isolate this exponential. So let's divide out the 173. You could change this to a decimal if you wanted to. I'm just going to wait and do everything at the end. Okay, and then to get t out of that exponent position, like the last problem, let's bring in ln, or you can bring in log, it doesn't matter. So put ln in front of both sides of this equation. Making sure you know that's of course is a fraction. Okay, and why do we bring in the ln? So that you can take this exponent and take this power and make it a factor. So just re-recording over here the left-hand side of the equation. And then putting the 0.046t in front of ln e. Right, and then to get t by itself, let's just divide out 0.046 ln e, which that's just going to be 1, but you might not see that right now. And those divide out, divide out, divide out. And so over here, I've also got to divide by 0.046 ln of e. So I've got t left. I'll put it on the left-hand side of the equation. And then in the numerator, ln of 329,000 divided by 173. You might want to kind of do this in parts, maybe get that answer. And then after you get that answer, divide by 0.046 ln of e, making certain to put this denominator in parentheses. Okay. And rounding to the nearest tenth of a year, I think I got 14.0 years, but let's go back and see what the question said, making sure we answered it. When will the population of the city reach 329,000? So since I got 14 years, I would say add 14 years to 1998, and that'd be 2012. So I'm not sure if you're going to be looking for the year 2012 or if you're going to be looking for 14.0 years. It really wasn't quite that clear. Okay. All right. Let's move on to 65 and 66. Solve the system of equations by the substitution method. All right, so on 65 and 66, for the substitution method, we kind of inspected both the equations, and we tried to isolate either the x term or the y term, one of those terms that had a coefficient of 1. We tried to isolate that and get that equation by itself. But what's kind of interesting about 65 is, and I might even try and do it on here. You can do it on notebook paper, but I think it's going to be pretty straightforward. Both equations are set equal to y, so how about if we set both equations equal to each other? So 2x minus 6 should be equal to 7x minus 7, since they're both equal to y. And then from here, it should be a pretty easy algebraic solve. And I'll add 7 and add 7. Looks like I get 5x equals 1, so x equals 1/5 when I divide both sides by 5. Well, that seems weird, that it'd be a fraction, but now let's find y. So to find y, we're going to insert 1/5 into either of the two equations. I'll just choose the top equation. So 2 times 1/5 minus 6. And so we'll have a calculator. So this product would be 2/5 minus 6. You can change them to decimals if you want, or if you got a common denominator of 5, this would be 30 over 5. And when you subtract 2 minus 30, you get negative 28 over 5. So I guess I needed more room than I thought. So the solution here would be positive 1/5 for your x and negative 28/5 for your y. And it might be 0.2 and negative 5.6, I think, for decimals. Okay. All right, 66 is the same type of problem. We're going to use the substitution method, and I think I've run out of room there, so I'm going to do 66 on notebook paper. So give me a minute to transfer that over. Okay, here we go. So using the substitution method, we just kind of eyeball both equations. We're looking for the one equation, or a equation, that has either an x or a y term with a coefficient of 1, and that looks to be in the second equation here. So we started there. That was our entry point for the substitution method. So let me first of all solve this bottom equation, isolate 1x. So I'm going to add the 5y to the other side. So what we can say is that this equation rearranged is actually x equals 5y. And then what we did is we went back to the other equation and we replaced in for that x in the other equation 5y. So now I'm going to come down here. So I got negative 5 times 5y plus 3y equals negative 22. Now I have just an equation in terms of y, so let me clean this up, solve for y, and then I'll be able to get back to x. So this is negative 25y plus 3y equals negative 22. Collecting these y terms, I get negative 22y equals negative 22. Let's divide by that negative 22 and divide by negative 22. And that looks like it's setting up to be a nice number, y equals 1. But remember, we've got to go back and get the x. So now that we know y, I would probably go back to this equation, inserting 1 here. So that means x is equal to 5. So my final answer is 5, 1. Okay, so for these next two problems, we're going to solve this system of linear equations by the addition method. So in that method, not substitution, we lined up, made sure all our x terms are lined up, our y terms, and our answers are lined up. And then we tried to eliminate either the x's or y's, depending upon what seemed to be the easiest. So for 67, it looks like I would probably want to eliminate the x's, because I can just multiply either the top or the bottom equation by a negative 1, and that would allow me to eliminate the x's. All right, focusing on eliminating the x's, I would just say to myself, let me multiply everything in this bottom equation by negative 1. So this is where I kind of drew a squiggles, because I'm not ready to add down. Let's record the 2x plus 7y equals 12 and distribute the negative 1 into every part of this problem. So negative 2x minus 2y equals negative 22. Now straight line, because now I can look down a column and cancel my x's, collect my y's, collect my constants. I think that's negative 10. Divide by 5. So it looks to be that y is negative 2, and then we're going to do some back substitution. So now choose any of the equations that you have. I'll just go to the first one. I'll write that down. And then wherever I see y, I'll plug in negative 2. Let me add the 14. I'm going to divide by 2. It looks like x is going to be 13. So the solution is the ordered pair 13, negative 2. All right, 68 is similar. Oh, maybe I should have done 68 because it's the more involved problem. But With 68 here, you could either choose to eliminate the x's or the y's, and I don't think there's one easier elimination than another. If you're going to eliminate the x's, then it looks like you're going to have to multiply the top equation by 7 to get 14x, but then the bottom equation, everything gets multiplied by 2 to get negative 14x. So just check the worked out solutions. It'll all be there. I think it's pretty straightforward. You just have an additional multiplication. Okay. All right, 69 and 70. Determine if the ordered triple XYZ is a solution of the system. I think I'm going to skip both of these for these problems. All you're going to be doing is inserting the x value of -1 and the y value of 5 and the z value of 1 into each of these equations. And when you plug these numbers in, do they add to, in this case, do they add to 5? And then you have to try these three values in for all three of the equations to see if they make a true statement. And then you can respond and say, yes, that is a solution. So I think the worked out solutions kind of provide maybe enough work there to understand what's going on. Let's move down to 71 to 73. Whew, now we have a linear system, 3 equations, and it tells us to use matrices. Well, we really have 2 choices here. We can use Gaussian elimination. Gaussian elimination. And that required us getting an augmented matrix and putting that augmented matrix in row echelon form. It's ones down the diagonal. Okay, and another way you can solve this is by using Cramer's rule. So, you know, whatever is your preference. Of course, it's multiple choice. If you're given a solution as one of the choices that have the values for X, Y, and Z, just start plugging and chugging to see which one works, if that's an available strategy. So we have Gaussian elimination with putting an augmented matrix in row echelon form, or it's going to be Cramer's rule. So I think we'll do one of each of them just to remind you about those 2 strategies. So I'll just do 2 of the 3 here, one of each with these different strategies. Okay, so 71. So I'll start there. And I might not be on the screen, but I will be in a minute. Let me transfer this over here. And I might say, I actually don't prefer either one of these methods in solving a linear system of 3 equations. What I would do is I would choose 2 equations and choose to eliminate x, y, or z. So for example, if I chose equation 1 and equation 2 and I eliminated the y's, I would get an equation with 2x plus 6z equals 24. And then I would choose another set of equations, probably the second equation and the third equation, and eliminate the y's there as well, and get 2 equations with 2 unknowns, solve those first, and then back substitute. To me, I'm less likely to make mistakes than I would when I do row echelon or Cramer's rule. Okay, but when they say solve the system equation using matrices, that's one of these 2 methods. That really doesn't imply what I just kind of talked us through, but like I said, that's my preferred method. It's multiple choice, do what you want, but we're going to revisit row echelon Gaussian elimination for this problem. So what we did is we wrote the augmented matrix. And then our goal was to get 1s down the diagonal with 0s here. So the first row is good. I've got a 1 leading off, so I really want to focus on getting this 1 to be a 0 and then getting that -1 to be a 1. So I think my first step is going to be to work on row 2. So let me keep row 1 and row 3 and re-record them. There's just too many places for me to make mistakes and transfer over an incorrect number. Okay, to make this 1 a 0, I'm going to need to get to a 0, I'm going to multiply row 1 by -1 and add it to row 2. So let's record that. So I'm going to take row 1 and multiply it by a negative and add it to row 2. So row 2 changes. So -1 plus 1 is 0. -1 plus -1 is -2. -1 plus 5 is 4. And that would be +2 plus 26 is 28. Okay, I'm still working on row 2. So let me re-record row 1 and row 3. All right, the 0 is good, so I want to change that -2 to a +1. So how about we take row 2 and we divide it by -2, which is the same thing as multiplying by -1/2. So let's take -1/2 of every element in row 2. So 0 times -1/2 is still 0. -1/2 times -2 would be +1. 4 divided by -2 is -2, and 28 divided by -2 is -14, looks like. Okay, so row 2 is good. Now we need to focus our attention on row 3. We need a 0, 0, 1. So row 1 and row 2 are good, so let's just re-record those. Okay, first things first, let's get this 5 to be a 0. Well, you don't want to work with row 2 in making this 5 a 0. Let's go to row 1. If you multiply row 1 by -5 and add it to row 3, that's going to accomplish getting this to be a 0. So -5 plus 5 is 0. -5 plus 1 is -4. -5 plus 1 is again -4. And -5 times -2 is 10. 10 plus -14 is -4. Okay. Still working on row 3. We need this -4 to be a 0. All right, so if I need this -4 to be a 0, I probably am going to work, now I'm going to work with row 2 because I don't want to change this 0, so it's good to have a 0 here. So let's multiply everything in row 2 by 4. So when I add, I'm going to get 0 here. So 4 times row 2 plus row 3. So 4 times 0 is still 0. 0 plus 0 comes over 0. 4 times 1 is 4. 4 plus -4 is 0. Good to go. 4 times -2 is -8. -8 plus -4 is -12. Yes. 4 times -14. -56 plus -4 is -60. And finally, we need that to be a 1, so I'm going to divide by -12. All right, so I'm going to take the last row and divide by -12 to make this a +1. So that's the same thing as multiplying by -1/12. Times row 3 only. So 0 times -1/12 is still 0. 0 times that number is still 0. And yeah, and then -12 divided by -12 is 1. And -60 divided by -12 is 5. All right, we've got 1s down the diagonal, so what does this tell us? Well, starting with the bottom row, this is x, y, this is z. We know z is 5. Moving up to the second row, we know this is 0x, that's 1y. 1y minus 2z equals -14. And the top row, that never changed. All right, back substitution, so z goes in here as 5. So y minus 2 times 5 is -14. Let's add a 10. Y equals -4. All right, so now we're going to plug in y and z here. So x plus -4, or x minus 4, plus 5 equals negative 2. What is that? X plus 1 equals negative 2. Subtract 1. X equals negative 3. So let's format this correctly. An ordered triple would be X, Y, Z. So this looks like this is our solution. All right, so that's what, 71? Okay, so that was Gaussian elimination, putting an augmented matrix in row echelon form to do back substitution. Okay, so let's look at one more. Let's look at solving a linear system with 3 equations using Cramer's rule. I think I'm going to start a new sheet of paper here. Okay. And we'll just do number 72 with that, which is probably a wise decision, because if you look at the second equation in problem 72, notice that there's no y term. We're going to be able to fill in a 0. So that's good for Cramer's rule anyway. And if you wanted to fill in a 0y here, that'd be fine. Okay, Cramer's rule, let's see. We need 4 determinants. Remind ourselves about that method. To get the x coordinate of that triple, it's the determinant dx over d. And then we've got y equals dy over d. And then likewise z. Okay, so let's go ahead and calculate the d determinant first. And that's just going to include the coefficients of the variable terms. So we don't look at the answers here. That's 3, that's 0, that's 1. 3, 0, 1, 1, 4, 1. Okay. So in Cramer's, well, to find this 3 by 3 determinant, I'm going to choose a row or column that has 0. So I'll just choose row 2. So don't forget your sign chart. We've got plus, minus, plus, and it alternates. So this is minus, this is plus, and this is minus. So the value of this determinant is found by taking negative 3 as our factor, multiplying it by its minor, cross out the row and column, recording the remaining values. Move on to the next factor, next element in your circled row, and that's plus 0 times some determinant that I don't care about, because I'm going to get 0 anyway. Let's go ahead and move on. Minus 1 times this minor. So cross off 1, negative 1, 1, and 4. Okay, so we've got negative 3 times, and then we've got the down arrow product minus the up arrow product 12. And that's all 0. And then I've got minus 1 times this 2 by 2 determinant. So that's 4 minus negative 1. This looks to be negative 13 times negative 3 is 39. And this in here is going to be 5. So that's going to be minus 5. So it looks like this is going to be 34. Doesn't look like a nice number so far, but hopefully all the other numbers will work out. Okay, so, all right, so let's find the dx determinant. Which means we replace the x coefficients with the answers. So 2, 2, 18, but we keep the y and z columns. I believe that's 3 and 1 and 1. I'm again going to choose row 2 because it has that 0 in it. So don't forget the signs right here. So it starts out negative 2 times negative 1, 3, 4, 1, plus 0. I don't care what that minor is, that all goes to 0. And then minus 1 again. Oops. What is that determinant? 2, negative 1, 18, and 4. All right, so that product is negative 1, and always record a minus and then multiply, and we get 12. Minus 1, 8 minus negative 18. So again, that's negative 13 times negative 2 is 26. This is 26 here, and that's minus 26. So that's 0, which is wonderful. Because if you think about it right now, if dx is 0, I'm going to put 0 here on top of 34, and 0 over 34 is 0. So our x-coordinate will be 0. If we could only be so lucky as to get zeros again in the other ones. Okay. All right, so dy, keep the original x coefficients, replace the y column with 2, 2, 18, and then keep the original z column. And we wiped out the 0 here, so it's just a matter of preference what row or column you want to choose. I'd probably choose something with the smallest numbers, but you know, it's certainly up to you. Maybe I would choose column 3, reminding myself that this is plus, minus, plus, and then setting that up. And I think at this point I will set this up, and then I'll walk away from this problem just saying that the dz determinant is calculated on the worked out solutions. And again, the dz determinant will have that 0 returned in there, so it'll be a little bit easier. All right, at least stopping or completing the setup here and then stopping. So positive 3, eliminate 3, 2, 1, 18. 3, 2, 1, 18. And then we have minus 1, 1, 2, 1, 18. And then plus 1 times 1, 2, 3, 2. 1, 2, 3, 2. And then from there, you can compute the 2 by 2 determinants and finish that up. And the worked out solutions will have that all on there. So, okay, so we'll just join back with the next problem in the next video.